Right, so in this video, we're going to be talking about the quantum mechanical model of the atom. This is actually a refilm, so if you've seen another video of me talking about this, you could kind of ignore that one. I realized that I made a mistake talking about some things that we're going to talk about in the next video, kind of blended them together and it might have been confusing. So stick with this video if you have already watched the other video. So again, we're talking about the quantum mechanical model of the atom. And the goals here, we want to be able to identify principal energy levels in an atom, state the energy trend among them. And then for the principal energy levels, we want to be able to talk about the sublevels, sketch the shapes of these things called orbitals, state the number of orbitals in each sublevel, and then talk about the restrictions of how many electrons we can put in those orbitals. And as I'm filming this, I realize something's wrong, and it's that I don't have my glasses on. So put those on so I could see, and let's get started. So just like we saw with Dalton's atomic theory, the Bohr model is kind of a simplistic model. It actually only works for hydrogen. And so going beyond that, there's more specific models that we can use. So in 1924, a guy named de Broglie said that matter in motion, like electrons, has properties that are normally associated with waves. And then Schrodinger, of Schrodinger's cat fame, if you know that, applied the principles of wave mechanics to the atom. And all of his calculations, which we're not going to go through in this class, yielded 4 quantum numbers that are used to identify electrons in a multi-electron atom. And so atoms other than hydrogen, of course, have multi-electrons. So this will be used for those atoms. And so here's kind of the takeaways in the top here from these quantum numbers. And what we can know is that each electron has a unique set of quantum numbers. We're going to talk about these, but they're used to identify the electron. So you have things like principal energy levels, which are very generic, or general, I should say. And then it gets more specific when we talk about electron orbitals and orbital occupancy. So here we go here. So here are our introduction to principal and sub-energy levels. And principal energy levels is what we've seen before with the Bohr model. So that is using the symbol here, N, okay? And that's N equals 1, 2, 3, 4, 5, etc. And generally, energy increases with increasing N. And the distance between the electron and the nucleus increases with increasing N. We saw that again with the Bohr model, where you had almost these orbits, if you would, that are increasing with increasing N, the radius of the electron and the nucleus. So this is general, and this is kind of the thing I had in the last video. We're going to be talking about some exceptions to this a little bit later in terms of energy with these levels, or the sublevels really. But generally, energy increases with increasing N, okay? And so the sublevels are, for any one of these principal energy levels, there are one or more of these things called sublevels. They're known as the S, P, D, and F sublevels, okay? We'll really only have to worry about the S, P, and D sublevels in this class. And the total number of sublevels within a given principal energy level is equal to N, the principal quantum number. So, for example, when N is equal to 1, we can only have one sublevel, and that would be the S sublevel, okay? So it would be 1S. So you just pick the first one. When N is equal to 2, okay, you can have 2S or 2P, okay? Similarly, when N is equal to 3, you can have 3S, 3P, 3D, okay? And I think you get the idea. You keep adding on to them. But the key is whatever the principal quantum number is, that's how many sublevels you can have, okay? And you just kind of count down the sublevels, 1, 2, 3, 4, okay, to have them all out. Now, for an element other than hydrogen, the energy of each principal energy level spreads over a range related to the sublevels. So this is something, again, we're going to be talking about a little bit in next week's video on chapter or section 11.4, how we can talk about the energies of these sublevels. But this is generally how it is. So 2s orbital is lower in energy than 2p, 3s is lower energy than 3p, which is lower energy than 3d, etc. Okay. So you're going to have this as a reference. And again, we're going to find a way to memorize this or to have a trick to recognize this in next week's video. And so here's just the sublevels plotted out here. So you have the 1s sublevel, 2s, 2p. This is as a function of increasing energy here. And this is just kind of illustrating what I just said on the left-hand side here. Okay, so let's go on to electron orbitals then. So remember, we were talking about general to specific. And so electron orbitals, what we can think about is it's not really possible to know at the same time both position of an electron, the position of an electron, and its velocity, according to the Heisenberg uncertainty principle, which we don't have to worry about, but for now you can just know that it's not possible. So there's no clearly defined orbits then, like the Bohr model would suggest. Right? In the Bohr model, you have the nucleus, which is like the Earth, and the electron is like the moon, right? Kind of orbiting the Earth. That's not really how it is. It's not planets around this orbit. Instead, what we really see is something known as an orbital, which is a region, which is shown over here, in space around a nucleus in which there is a high probability of finding an electron. Excuse me. And that's the key, that there's just a really good chance that we're going to find an electron there. So that region of space around a nucleus we call an orbital. And so these orbitals then have different shapes actually. So each sublevel has a number of orbitals that depends on the sublevel quantum number. So here's it listed over here. So S sublevels have 1 orbital, P sublevels have 3 orbitals, D sublevels have 5 orbitals, and F sublevels have 7 orbitals, okay? And each of these orbitals can either have 0, 1, or 2 electrons, but they can't have more than that. Okay, they can't fit more than 2 electrons. It's either 0, 1, or 2, okay? Never more than 2. So over here on the right are shapes of these orbitals. Okay, so this is an s orbital, and it kind of looks like a sphere. All right, and over here we have p orbitals, and there's 3 of those. And it might be hard to see. I think I said to z, but this is an XYZ axis here. So these p orbitals are aligned on the different axes. So this is a px orbital, this is a py, this is a pz. Okay, again, just lined along these different axes. So the p orbitals kind of look like a dumbbell, if you will. The d orbitals are down here. Okay, there's 5 of them, and most of them kind of look like these clovers. Okay, so kind of like a clover shape. That's a d orbital, except for this guy that kind of looks like a donut. Okay, so he's interesting. Won't have to worry about him too much, but this is just to give you an understanding. These are the d orbitals of what these orbitals look like. And we'll be talking more about them as we go through this chapter. Okay, so here's a summary so far of the quantum mechanical model of the atom. So we have principal energy levels, like we said, which we've talked about before, which is 1, 2, 3, 4, 5, 6, etc. And then there's these sublevels, and the number of sublevels we have corresponds to the number of principal energy levels. So if we have n equals 3, we can have 3 sublevels, for example. And then for each sublevel, there's a certain number of orbitals that we can have. So for S sublevel, there's only 1 orbital. P sublevel, there's 3. D sublevel, there's 5. F sublevel, there's 7, etc. And each one of those can have 2 electrons in it, okay? So to get the maximum number of electrons, you multiply the number of orbitals by 2, and these are the maximum number of electrons per sublevel, shown here, okay? So you can have this for reference, of course. Let's do some problems where we go over this and kind of check our knowledge. Okay, so we're going to answer each of these true or false. So A is there is no D sublevel, when n is equal to 2. So if you write this out, right, we have S, P, D, and F, right? And remember, the number of sublevels we can have corresponds to the principal energy, or the principal quantum number. So when n is equal to 2, we can only have 2 sublevels, and so you only pick the first 2, okay? You always just go S first, that's 1, then P second, then D is third, actually. So this statement is false, or is true. Whew. Listen this up. It is true there are no D sublevels when n is equal to 2, all right? So I'll say that again because I'm messing it up again. Ooh, it's too early in the morning, but there are no D sublevels when n is equal to 2, okay? That is a true statement. Okay, next, there are 3 p orbitals at the third principal energy level. Well, if you go back here, there are always 3 p orbitals. That's the maximum we can have. So even when n is equal to 3, okay, the third principal energy level, we could still have 3 p orbitals. So this is also true. Okay. And then the next one is there are 5 d orbitals in both the fourth and the fifth principal energy levels. Well, again, for d orbitals, we can always have 5, right? No matter what principal energy level we're at. So this is also true. They're all true. Okay. So this is, again, just a brief summary of the quantum mechanical model for the atom. In the next video, for next week, we're going to be talking about electron configuration. See you then.